Hey everybody, Professor Davis here. I'm going to talk to you for just a few minutes about the aldol condensation. And specifically, I'm going to show you how this reaction proceeds through an acetone and benzaldehyde reaction mixture. This is a classic example of the aldol condensation. It's easily run in labs, and you'll probably encounter it in your text as well. So as I mentioned, we're using acetone and benzaldehyde as reagents here, and hydroxide as a catalyst. And when you do that, the acetone and benzaldehyde can combine through a process known as an aldol condensation to form a molecule of benzalacetone and also a molecule of water. So this is the source of the condensation part of the reaction's mechanism name. So we make a little bit of water and we also make our new product. Now this mechanism can continue, and in this case a benzalacetone molecule can react again with another benzaldehyde because it still has an acidic proton, and create dibenzalacetone and water in a second condensation. And you'll no doubt be made aware of this when the time comes, but for now we're just going to focus on that first condensation step so that we can take one look at an aldol condensation happening. But keep in mind again that this one can actually go through two steps. Okay, so let's begin our discussion about this particular aldol condensation reaction by putting the mechanism up. So I'm going to take you step by step through this mechanism, and I'll highlight each step on the bar here as we go. So we're going to begin with a ketone, an aldehyde, and a base, as we would for any crossed aldol condensation. In our case, the specific ketone is acetone, the specific aldehyde is benzaldehyde, and the base we'll be using is hydroxide. Again, these are very common choices for a very simple example, but remember, you can have different molecules go through the same type of condensation. So I'm going to have my hydroxide react to start off with the most acidic proton in the system. Do you see where it is? Yeah, you might not notice it right away because it's on a carbon, but that CH bond is actually somewhat acidic because the resulting carbanion is stabilized as an enolate. So let's have our hydroxide react with that proton, whose pKa is about 20. All right, our hydroxide comes in and removes the acidic proton to form water. Now, this may not pass the smell test for you right away, right? Because we know that the pKa of water is about 16. So I've suggested to you that this reaction is going to take an acid with a pKa of 20 and react to form an acid with a pKa of 16. And we know that that's not going to happen favorably. This equilibrium is going to be well in favor of starting materials. But we've got a guy on our side who's going to allow us to do this, right? Le Chatelier's principle says that as long as I can consume all of that carbanion in an irreversible step later, then I won't have to worry about it. My equilibrium will continue to feed me this carbanion until it's consumed. In our next step, we're going to bring our aldehyde in. So let's move that a little bit closer. Now, the second step of an aldol condensation is a nucleophilic attack between our newly generated carbanion and our aldehyde. So the most nucleophilic site in the system should be pretty easy to find, right? That would be that carbon there, which has a very dense negative charge and a lone pair to give up. And then the most electrophilic site, of course, is going to be the carbonyl. Carbonyls are great electrophiles. And in this case, although we're having a nucleophilic attack, we're not going to have a leaving group per se, and that's because instead we have these pi electrons of the carbonyl, which are very easily withdrawn to the oxygen to avoid making a pentavalent carbon. So let's watch everything in action now. So our nucleophilic attack will take place, and withdrawal of pi electrons will be simultaneous. Great. So now we've made a tetrahedral intermediate. And this tetrahedral intermediate is also somewhat basic. So it's going to take a proton from the water that we generated in the first step. So let's do that now. Our water is going to come in and protonate our new tetrahedral intermediate. In doing so, we create something called a beta-hydroxy ketone, so named because the beta tells us that our functional groups are two carbon-carbon bonds apart, and of course the two functional groups are a hydroxy group and a ketone. Now, beta-hydroxy ketones are dehydrating machines. Because of the way that they're oriented, you can deprotonate that alpha carbon adjacent to the carbonyl and have an elimination reaction produce a resonance-stabilized species, specifically an enone. So let's watch what happens when the hydroxide moves up there and kicks off this E2 reaction. Our hydroxide's moved into position, and now it's going to deprotonate the alpha carbon, causing a cascade of electron flow which leads to our enone. At the end of this, you can see that we have regenerated our hydroxide catalyst. We've also created our mole of water. So we've created our base-catalyzed condensation reaction product. Now, benzaldehyde is used often in this reaction because not only is there an enone motif in this molecule, but I'm going to expand our collapsed benzene ring here, which I've used pH as an abbreviation for. And when I place that there, you can see why this reaction really runs well. This final step creates a highly conjugated compound, which has lots and lots of attached pi system through which electrons can move. So it's this resonance stabilization in the product that makes the final step of an aldol condensation like this one irreversible. And this, of course, is a synthetic organic chemist's dream. This is a reaction where all the other disfavored equilibria leading up to it don't matter, because that last step is irreversible. And once product forms, it's formed for good. So this should be a reaction that's easy to run and achieve high yields. And again, if we want to continue, we can add another benzaldehyde molecule to the other side of our new product and create dibenzyl acetone. I'm going to let you do that mechanism on your own, and that's all for now. I'll see you next time.